Orbiting solar panels could power entire cities on Earth. The vision of space solar power, often abbreviated as SBSP, begins with deploying immense solar power satellites in orbit. These satellites would capture sunlight, free from the impediments of cloud cover or atmospheric interference that limit solar collection on Earth. Unlike terrestrial solar panels, which face challenges such as nighttime darkness, space-based systems would benefit from near-constant exposure to the sun. The energy collected would be converted into microwaves or lasers and transmitted through the atmosphere to receivers on Earth's surface. The concept isn't just theoretical. Its potential applications have sparked interest since the 1970s, when groups like the L5 Society advocated for SBSP as a civilian energy solution, and later recognized its dual-use potential for missile defense, influencing the 1980s Strategic Defense Initiative. More recently, significant strides have been made, such as the U.S. Naval Research Laboratory's test of solar power generation in a satellite in 2020, and Caltech's Maple project successfully demonstrating power beaming to Earth in 2023, transmitting an effective isotropic radiated power EIRP of 3.2 watts. However, the path forward is not without hurdles. The cost of launching materials into orbit remains a barrier, as does the challenge of safely and efficiently transmitting energy over vast distances. Yet, as countries like Japan and China actively pursue space solar power, the dream of harnessing the sun's energy from orbit grows closer to reality. Could these developments signal a new era of clean, sustainable power from the final frontier? One of the most compelling advantages of space-based solar power lies in its ability to harness significantly more energy than terrestrial systems. Freed from the atmospheric barriers of reflection and absorption, solar power satellites can capture a nearly uninterrupted flow of sunlight. Unlike Earth-based solar panels, which are hindered by weather conditions and the cycle of day and night, space solar systems revel in the darkness of space, where night is but a fleeting visitor. The satellite's ability to constantly face the sun maximizes their efficiency, allowing them to convert sunlight into a form that can be beamed down to Earth, such as microwaves, without the losses seen in traditional systems. Beyond theoretical promise, this technology has seen pivotal tests. The U.S. Naval Research Laboratory's 2020 satellite trial and Caltech's Maple project in 2023 mark significant strides. These advancements not only confirmed the practical feasibility of transmission, but also inspired ongoing research and funding. The strategic deployment of space solar power is not just about generating electricity. It intersects with defense technologies, as seen in historical initiatives like the Strategic Defense Initiative and modern projects such as the Golden Dome program. As we delve deeper into these dual-use applications, we'll explore the profound implications and potential controversies of this powerful synergy. Isaac Asimov's 1941 story Reason painted a vivid picture of a world where solar energy could be harnessed in space and beamed back to Earth. While it was a work of fiction, Asimov unknowingly laid the groundwork for a revolutionary vision, one that scientists would take seriously decades later. Fast forward to 1968, when the SBSP concept was first articulated, and then to 1973, when Peter Glaser secured a pivotal patent for transmitting power from space to Earth using microwaves. The potential of space-based solar power was promising enough that NASA and the Department of Energy launched a comprehensive investigation into its feasibility in the late 1970s. They delved into every aspect from resource requirements to public acceptance, meticulously assessing the engineering challenges and potential impacts. Yet the high costs and technical hurdles led to a discontinuation of the project in the early 1980s. Despite these setbacks, the dream of harnessing solar energy from space persisted. Today, with renewed interest and funding, nations like the US, Japan, and China are racing to turn Asimov's fiction into reality. As we look ahead, we encounter a fascinating question. What might the success of space-based solar power mean for our planet's energy future? In the 1970s, the vision of harnessing the sun's power directly from space began to capture imaginations and inspire technological exploration. The L5 Society championed space-based solar power as a civilian energy solution, but it quickly became apparent that the technology held potential military applications as well. The idea of using it as a directed energy weapon played a significant role in the Strategic Defense Initiative of the 1980s. Physicist Lowell Wood, an influential figure in SDI, was among those who initially explored these dual uses. Pioneering efforts date back even further to 1968, when Peter Glaser first described the satellite solar power system. By 1973, he had secured a patent for transmitting power from space to Earth using microwaves. NASA, recognizing the promise despite formidable challenges, commissioned studies to delve deeper into the concept. With support from the Department of Energy, extensive evaluations were conducted to understand the feasibility and implications of such an ambitious project. Yet, political shifts in the 1980s curtailed these explorations. The Office of Technology Assessment advised caution, citing gaps in technical understanding and the high risks of moving forward without further research. Today, as we reflect on these early endeavors, we consider anew a world where space, rather than Earth, could be the primary source of our energy. How far have we come since those pioneering days? Space-based solar power presents a fascinating vision of clean, constant energy, but the path to realizing this dream is fraught with challenges. Technically, the transmission of energy from orbit to Earth without physical wires remains a hurdle. The most promising designs involve wireless power transmission, converting energy into microwaves or laser beams. Yet, the conversion inefficiencies and the vast antennas required on the ground pose significant engineering and land use challenges. Economically, the cost of launching the necessary materials into orbit looms large. Although technological advancements have reduced space launch costs, deploying massive satellite arrays remains expensive. The lack of experience in undertaking projects of this magnitude in space is also a substantial barrier. Environmentally, long-term exposure to space conditions could degrade the solar collectors, while large ground-based antennas demand significant land resources. However, contrary to the fears often portrayed in fiction, proposed beam densities are designed to be non-harmful to human life if the energy transmission deviates from its intended path. Despite these obstacles, nations like Japan, China, the US, and others are actively pursuing SBSP, driven by its potential to provide sustainable energy. But can we overcome these formidable barriers to unlock a new era of limitless power? Join us as we explore the innovative solutions emerging on the horizon. The promise of space-based solar power is stepping closer to reality through modern efforts by institutions like the California Institute of Technology, Caltech, and the U.S. Naval Research Laboratory. In May 2020, the Naval Research Laboratory took a historic step by testing solar power generation in a satellite, marking a significant leap toward harnessing energy from space. Building on this momentum, Caltech has also been pioneering in this arena. By August 2021, they announced plans to launch a space-based solar power test array by 2023. This initiative has been largely fueled by the vision and generosity of Caltech trustees Donald and Brigitte Bren, who have contributed over $100 million since 2013. The future seemed even brighter in 2023 when Caltech's Maple project successfully demonstrated the ability to beam energy back to Earth. The project transmitted power at a level far below commercial satellites, yet it proved the concept's viability, detecting a signal of about -45 dBm, or less than a tenth of a microwatt on the ground. While these efforts are still in their infancy, they illuminate a path forward. Could these breakthroughs inspire a new race to capture the sun's power from orbit? The ambitious strides by countries around the globe are setting the stage for what could become a new era of energy. As nations rally around the promise of space-based solar power, the global stage is abuzz with activity. Each country brings its vision, challenges, and innovations to the table. Japan, for instance, has embedded space solar power into its national objectives under its Basic Space Law. The Japan Aerospace Exploration Agency, or JAXA, is meticulously charting a roadmap to commercialize this transformative source of energy. Across the East China Sea, China is racing ahead with ambitious plans of its own. The China Academy for Space Technology has already laid groundwork for a testing base, signaling their resolve to lead in practical space solar power deployment. By 2035, China envisions launching a colossal 200-ton station capable of channeling megawatts of electricity back to Earth. In Europe, the European Space Agency is also actively involved, weaving together a tapestry of international ideas and expertise. Each of these efforts underscores not only a race for technological supremacy, but also a shared commitment to a cleaner, more sustainable future. The pursuit of space-based solar power is gradually becoming a collective endeavor, where collaboration may be just as crucial as competition. But as each nation pushes the envelope, what unforeseen challenges and opportunities might await in this stellar quest? As space-based solar power emerged as a promising avenue for clean energy, its dual-use potential as a weapon also came into view, casting a shadow over its development. In the 1970s, visionary groups like the L5 Society championed SBSP for civilian energy needs, but soon recognized its possible use in missile defense systems. This dual potential influenced the 1980s Strategic Defense Initiative, where architects like physicist Lowell Wood, who had ties to L5, explored its military applications. This overlap of civilian and defense interests continues today, with orbital power and directed energy transmission being integral to modern missile defense strategies, exemplified by the upcoming 2025 Golden Dome program. The dual-use nature of SBSP poses significant challenges in international collaboration and regulation. As countries advance their SBSP capabilities, the line between peaceful energy projects and military applications blurs. In May 2020, the U.S. Naval Research Laboratory made strides with its first satellite test of solar power generation, highlighting ongoing interest. Meanwhile, in 2023, Caltech's Maple project demonstrated power beaming to Earth, but with power levels far lower than commercial satellites, raising questions about scalability. As nations invest billions into this technology, the delicate balance between innovation and weaponization plays out on a global stage. How will this tension shape the future of solar power from space, and what global frameworks might emerge to manage its potential? As we peer into the future of space-based solar power, the implications of a viable SBSP system are profound. The potential for continuous energy collection, unhindered by atmospheric interference or the cycle of day and night, presents an unprecedented opportunity to redefine how we power our world. The ability to efficiently transmit energy from orbit to Earth, transforming sunlight into microwaves or laser beams, could revolutionize our energy infrastructure. However, achieving this vision is far from straightforward. The technological challenges are significant, from the sheer scale of the required infrastructure to the inefficiencies in energy conversion and transmission. Additionally, the vast land required for ground-based receivers, known as rectennas, poses questions about land use and environmental impact. Yet these obstacles have not deterred nations worldwide, with countries like Japan, China, and the United States actively pursuing SBSP technology. China's ambitious roadmap anticipates launching a substantial space power station by 2035, signaling a global race towards this new frontier of energy. As we stand on the cusp of this transformative era, one question remains: how will we navigate the complex interplay of innovation, environmental stewardship, and international collaboration to harness the full potential of space-based solar power?